we're looking at the lab for Unit 2 in chemistry, which is disturbing the equilibrium. So this is the introductory page. It has some good information on it. Remember that equilibrium, this equilibrium constant here shows the ratio of concentrations. That's what the brackets mean. Brackets indicate concentration of products to reactants, okay? So this KEQ, which is the equilibrium constant, always wants to stay the same. So if the amount of reactants changes, then the equilibrium will shift to make more products so that this ratio can always stay the same. And vice versa. If you, let's say, take some product away, the equilibrium will shift to make more product because it wants this equilibrium ratio to stay the same. So in this lab, you're going to see how this occurs, okay? Now, to set up an equilibrium constant expression, you're always going to put the concentration of the products over the concentration of the reactants. So if you have not seen this yet, you'll see that this animation shows you this setup. You'll notice the brackets for the reactants, the concentration of the reactants go on the bottom and the products go on the top. Any coefficients you have will be the exponent, okay? The other thing you should notice is that you're multiplying these concentrations here, whereas this plus sign means you add nitrogen gas to oxygen gas. Here you're multiplying the concentrations, which is a number value. And if you had, let's say, a coefficient in front of any of the reactants, that would also be an exponent for that substance in the equation. So what does it mean for chemical reactions to be at equilibrium? It says if a reaction is at equilibrium and you add more reactants, the system will be pulled away from equilibrium and the concentration of products over the reactants will no longer equal the KEQ, okay? So then the equilibrium will what we call shift to restore the equilibrium, okay? So Le Chatelier's principle states that if you increase the concentration on one side of the reaction, the concentration of the other side will increase so that you can restore the KEQ value. All right, so that's what you're going to be looking at in your lab today. How will you observe equilibrium? You're going to observe a reversible reaction that involves bromothymol blue, which is a pH indicator, okay? So bromothymol blue will be a yellow color if it's in acid, and it will be a blue color if it's in a base, okay? So yellow in acid, blue in base. So when you have this system of acids and bases at equilibrium, and then you add, let's say, more acid or you add more base, you're changing the equilibrium by changing the pH of the solution. So go ahead and read through this carefully. It has a lot of good information. It says a solution with a low pH has high concentration of hydrogen ions. A solution with a high pH has low concentration of hydrogen ions. Okay, so that's how we're going to be shifting the equilibrium, by following the hydrogen ions back and forth. In your pre-lab, you have 4 questions to answer. The first one says, what does stressing an equilibrium system mean? How is stress applied? So remember that if you go back here, you'll see it talks about the concentration. So think about the concentration when talking about stressing the equilibrium. And then the second question says, here's a reversible reaction with a pH indicator, bromothymol blue. Write the equilibrium expression for this reaction. So what you want to do is write KEQ equals, and then you're going to put the concentration of the products in the numerator and the concentration of the concentration of the reactants in the denominator. It's always products over reactants. Question 3, what direction do you predict the addition of an acid to the solution containing bromothymol blue will drive the equilibrium? Explain your prediction in terms of Le Chatelier's principle. So this is the acid. So it's asking what happens when you add more acid? Is this equation, is this equilibrium going to shift towards the products to make more product or towards the reactants to make more reactant? So remember, Le Chatelier's principle says the equilibrium will shift to undo the change. So if you add more acid, which is this substance here, how will the equilibrium shift to use up the extra acid that you've added? That's question 3. Question 4, what direction do you predict the addition of a base to the solution containing bromothymol blue will drive the equilibrium? So here is your base. That's your base product, okay? So what happens if you add more of this? Which way will the equilibrium shift to use up the extra base you've added? Okay, so that will be your pre-lab. Please don't forget to do your pre-lab. I see a lot of labs where the pre-lab is missing and I hate to take points away. So make sure you answer these questions before you get to the lab. Here is your lab. Once again, the introduction is important, okay? So it talks about reversible reactions, both forward and backward directions. So this is the forward direction of this reaction, N2O4 yields 2NO2. That reaction can also run in reverse. Okay, this is the reverse of 7.1, this reaction here. And so with reversible reactions, we can just use a double arrow to indicate that the reaction is reversible, just like in 7.3. All right, so once you have a reversible reaction, you have a system that's at equilibrium. Le Chatelier's principle is applied. If a chemical system at equilibrium experiences a change in concentration, and that could be the temperature, the volume, the pressure, or the concentration, sorry, I missed that one, the equilibrium shifts to counteract the imposed change. Okay, it's going to shift to use up the extra stuff you've added, or it will shift to add more stuff if you've taken something away. Okay, so again, here's the reaction you saw from your pre-lab. The procedures are here. You obviously don't have to do the procedures because you are doing the dry lab. So for the dry lab, they've given you the data. Okay, they've given you the data. So what you're going to do is look at the reactions in these different well plates, right? A1, A2, A3, and then A1, A3. So what happens is A1 is indicator in HCl, right? Obviously, it's yellow in color with bromothymol blue because bromothymol blue is yellow in an acid, and this is just acid. But here, you're adding a base. KOH is a base. It has hydroxide in it, okay? When you add the base, it turns blue. Here is A3, indicator, and KOH. So KOH is the base. It is initially blue. And then here, you add the acid. Notice, and it turns yellow. Then you take that reaction, this reaction, and you add more hydrochloric acid. Yellow, and then for A3, you add KOH again, and it turns blue. So you can see like KOH was blue, turned yellow. Oh my goodness, sorry guys. Look, it turned yellow and then turned blue again. Okay, so that's an equilibrium shift. And so you're going to be answering these questions based on this shifting equilibrium back and forth. So I just wanted to make sure that you understand what this table says. there are three wells, A1, A2, and A3. A2 is the control. That's why nothing is being added to A2 in the experiment. So you'll notice that in A1, you start with hydrochloric acid, you add KOH, and then you add hydrochloric acid again. So you're shifting the equilibrium back and forth. And in A3, it's the opposite. You start with KOH, you add hydrochloric acid, and then you add KOH again, shifting the equilibrium back and forth. So you will use your understanding of equilibrium and Le Chatelier's principle, which is what happens when you stress the equilibrium, to answer these questions. Okay, if you have questions beyond what this video provides, please email me and we can schedule a time to meet.